question has Manuel Rivera, Mr. Day, New Point Topology. And you going to send one?
I was.
You now live in Miami, right?
Right.
Okay.
But that path was more convoluted, right?
No, I didn't put everything.
I know.
You want me to put
Not
everything?
homotopic.
It's not at all.
I didn't realize that you could do more than be connected stuff.
Okay.
Okay, so thank you for the invitation. It's a pleasure to be here and see many friends and colleagues. So what I would like to share with you today, this new point, a new conceptual point in topology, which puts abstract homotopy theory and the fundamental group in the same package. So going straight to the point, what I would like to discuss today is the sense in which the algebraic structure of the singular chains on a space in topological space determines the fundamental group and much more. Okay. By much more, I mean the entire homotopy type. But it's really this fundamental group part that needed a novel idea in homotopy theory. Okay, so I'm going to concentrate on this. I will make this a precise statement.
And it's also algebraic structure should be in the left.
Okay.
The singular change in terms of space.
I agree. I will make this a precise statement, and as I said, it uses a new idea in homotopic theory. And the way we finally understood this point was by first taking a close look at an old result of Frank Adams, the theorem of Frank Adams from the 50s, I think it's 1956, so almost exactly 6 years ago. And we will take a close look at this theorem from the perspective of homotopy theory of coalgebras. So by homotopy theory, I mean a framework in which you treat certain class of maps as if they were isomorphisms. Okay, so maybe I should say this deals with inverting certain class of maps, which we call weak equivalences. An abstract framework for doing this. And by coalgebras, well, let me quickly give a definition of a coalgebra. So if K is any commutative ring, a coalgebra is a K module. Let's call it C, with a linear map from C to C tensor itself over K, satisfying certain properties like the dual property of associativity, which we call co-associativity. And we will also require this to have a co-unit, which is a map projection to the ground ring, satisfying the dual property of being a unit. Okay. So this is kind of the ingredients that we use to understand this point. And there's a general philosophy I would like to emphasize before I start going into more details. And the philosophy is the following. So this philosophy will be this will serve as an example for this philosophy. So the philosophy is the following. So geometric information of a geometric space may be expressed algebraically in terms of geometric chains on that space. Right, in terms of chains. And we want to apply homotopy theory to this algebraic structure. But before applying homotopy theory, we have to either adjust it, the algebraic structure in some specific sense, or enhance it. And we will see examples of both, of what I mean by both of these things in this example. And once you do that, you can apply homotopy theory, meaning treating a certain class of maps as if they were isomorphisms. And then, once we have a suitable homotopy theory for our purposes, we can try to find small models that are equivalent to our original algebraic structure in order to compute, to make computations. Okay, so this is the guiding philosophy. And today we will see an example of doing this with homotopical information. But our main motivation is actual geometric information. For example, we want to start with a topological manifold and be able to express an algebraic structure that determines the manifold structure of two homomorphisms, for example. That's our motivation, but today I'm going to give an example in the homotopical setting. Good. So, okay. So, associated to any space, we can consider its homology groups. So, let X be a path-connected space. Let's fix a base point. Associated to any space, we can consider homology groups. Let's say singular homology with integer coefficients. This is a graded group. We could ask the question, does this determine the fundamental group of the space? And we know the answer is no. In particular, we know that the first homology group of the space is the abelianization of the fundamental group. The fundamental group of P, right? And we know that this does not determine the fundamental group. For example, the wedge of two circles and the torus have different fundamental group, but same abelianization, right? So when we pass from chains to homology, we forget information, right? So we may ask the same question at the level of chains. So what about chains? What if we consider chains? I have to say, considering chains as what, right? So let me quickly remind you a little bit of singular chains. Singular chains. So we're going to use a particular model of singular chains. So I'm going to denote by Cn of X and B. This is the free abelian group generated by continuous maps from the n simplex to X, which send the vertices of the simplex. So sigma sends the vertices of the simplex to B. So I'm going to denote by C star of XP, this graded group. And it turns out that these reduced chains are quasi-isomorphic to the usual singular chains, since our space is path connected. So you have a boundary induced by the usual singular chains boundary, and this inclusion map is a quasi-isomorphism. this follows from the fact that we're working with a connected
That's
space.
the first time you used the word quasi-isomorphic.
Right, so a quasi-isomorphism, I mean a map of chain complexes compatible with the differentials which induce an isomorphism after passing to homology. So it's not quite an isomorphism at the level of chain complexes, but it somehow behaves like an isomorphism. Okay. So this is a chain complex, but it's more than a chain complex. There's a coalgebra structure on it. Okay. So it's called the Alexander-Whitney. I'm going to abbreviate by AW, diagonal approximation. This is a coproduct. That's a map from C to C tensor C. And it's defined as follows. So we have a singular simplex, a singular n simplex. We send that to the following sum of tensors. We take the simplex and we can restrict that to, we take the singular simplex sigma, and that can be restricted to the first I-dimensional face of this n simplex. That gives you an I simplex tensored with the last n minus I dimensional face, which I'm going to denote as follows. I here ranges from 0 to n. We define this on generators, extend linearly, and this defines a differential graded coalgebra, meaning that the coproduct is compatible with the differential. In other words, it's a map of chain complexes. Also, the coproduct is co-associative. And moreover, it's not strictly co-commutative. If you flip these terms, you don't quite get the exact coproduct, but it's co-commutative up to homotopy. Okay. And moreover, if any choice of homotopy can be also flipped here to get another homotopy. How are these two related? They're related by another choice of homotopy, and so on. Okay, so I'm going to write that as infinite homotopy co-commutative. Okay, so there's an infinite hierarchy of homotopies. Hierarchy of homotopies describing this co-commutativity. Okay. In particular, note that this coalgebra is connected, meaning that C0 has a single generator. It's pointed. And moreover, note that the generators of C1, singular one syntheses, what are these? These are, it's generated by all loops based at B, right? By this condition that the vertices go to B. So generated by all loops based at B. So how can we algebraically extract the fundamental group from all the loops that are here? So the amazing observation is that we can do that from the algebraic structure, the coalgebra structure of the chains. Okay? All loops are here, and now we extract the fundamental group from this structure. Okay, so that's what I want to describe. So, okay, so this construction is functorial. It's natural with respect to maps of pointed spaces, and therefore defines a functor from the category of topological spaces, which are pointed and path connected. I will denote path connected pointed spaces by this symbol. Two DG coalgebras with this infinite homotopic commutativity. That's our first construction, this functor of singular chains. Good.
Co-associativity is just assumed in the language like this.
Co-associativity is just assuming what I mean by DG coalgebra. I mean co-associative coalgebra. Okay. Okay, good. Now, recall that we know from homotopy theory that the homotopical properties of a space can be formulated in terms of topological groups. Okay? Not quite topological groups, but up to homotopy. So I want to introduce a new construction called the base loop space. Okay. So there's a functor, which I will denote by omega, takes a pointed connected space and outputs, well, let's say topological monoid. There is a topological space with a continuous multiplication, which is associative, and it has a unit. Okay. So let me describe this construction. So you take a pointed connected space, and you will send it to the monoid, which I will denote by omega b of x, which as a set is the following. It's a set of loops based at b, but I'm going to consider the following particular model. So it's pairs gamma r, where gamma is a map from the interval from 0 to r to x, sending the endpoints of this interval to b. Okay. This becomes a space with a compact open topology. Becomes a topological space. Compact open topology. And moreover, you have a continuous multiplication given by concatenating loops, right? You have two loops. You can concatenate them. You have two loops. You can do one first and follow the other to obtain a new loop in this space. And this is strictly associative. Note that I've taken a parameter here. This makes it strictly associative, a strictly associative monoid. And you have a unit given by the constant loop. Okay. Maybe I should call it identity. Given by the constant loop at b, which is defined when r equals to 0, 2x. Good. So recall that we have that the case homotopic groups of your space are isomorphic to the case minus 1 homotopic groups of the base loop space. Let's take the identity as a base one. They're all positive integers. And moreover, note that the zeroth homology of this space.
Can you explain the k equals 1 case? Up there.
K equals 1. So the fundamental group is given by the path components of your base loop space.
And why is it a group? Why does it have a group structure?
Well, it's induced by this concatenation of loops, and then your inverses are given by following a loop, reversing the orientation of a loop, right? If you do that, you get something that's homotopic to the identity. When you pass through homotopy, it's equal to the identity. So the H0 homology of your base loop space, it's isomorphic to the group ring of the fundamental group. So it's a group. This is generated, freely generated by the elements of your fundamental group, and you can put a ring structure induced by the ring structure of Z and the ring and the multiplication in your group. Okay. So this is an isomorphism as algebras. So I will come back to this point because there's more structure than just algebras here. Okay. So in 56, Adams modeled this passage algebraically. Okay. So as we saw here, to any pointed topological space, we can associate a coalgebra. We could ask, is there an algebraic construction which corresponds to this base loop space construction defined purely algebraically at the level of coalgebras? And that's the Kovar construction. So, Adams' Kovar construction. This is 56, as I said. So Adams constructed a functor which takes, well, let's assume we start with a connected differential graded coalgebra. And this construction will output an augmented differential graded algebra. Augmented means it's equipped with a natural map from the algebra to the ground ring. And this construction in particular produces a free algebra. Okay, so let me describe this construction. So you start with a differential graded coalgebra. So that's the data of a module with a differential and a compatible coproduct. And so the underlying module is a free module generated by C. So I will denote it as follows: the tensor algebra on C. And I'm going to take the positive part of C. That's what I mean by this symbol. So in particular, the generators here are monomials of generators in C, right? So generators look like monomials of generators in C. Each sigma I is a generator in C. And I'm going to put a differential given
the
on...
algebra generators are monomials and the linear generators of C. Is that what you mean?
Yes, monomials and the linear generators of C. I'm going to use the data of the differential and the coproduct to put a differential in this free algebra. Okay? How do I do that? I basically take the sum of these maps and I extend them as a derivation by Leibniz rule. Okay? The fact that the coalgebra, the underlying coalgebra is co-associative, and the fact that d squared equals to 0 implies that this new differential squares to 0.
Do you have to change the parity of the grading?
Yes. So let me describe the grading that we give to this graded module. So the degree, let me write it here. This has a special grading. The degree of a monomial is given by the sum of the degrees in C of each generator minus the length of the monomial. Okay? That's the same as taking the free algebra on the shifted module shifted by -1. So I include a shift for every term in your monomial. Right? So maybe I can write that here. S to the minus 1 means the shift. So in particular, something of degree 1 becomes of degree 0. Okay? Just as loops, which are one-dimensional things here, become points here. Okay? Good.
That minus one is up there in your pi table.
Right, exactly. So what's the theorem of Adams? Well, he proved that this Colbart construction is modeling this base loop space construction under certain hypotheses, connectivity
Is
hypothesis.
there a map? Do you have a map defined already now without any hypothesis?
Yes, we do. I'll state it.
Okay.
So the theorem of Adams, which relates these two constructions, the following. There exists a natural map. So for any connected space X, as we're assuming, there exists a natural map of differential graded algebras. Let's call it theta from the Colbart construction, which I'm using bold omega, on the chains, singular chains on your space X, to the following particular model for the following particular homological model for the base loop space. You take singular cubical chains now in the base loop space. So the base loop space is a topological monoid. When you take chains, you obtain a differential graded algebra. Adams constructed explicitly and geometrically a natural map of differential graded algebras, which is a quasi-isomorphism. Again, this means that it induces an isomorphism in homology under the hypothesis that the space is simply connected. So, the proof uses spectral sequences. Basically, it's a comparison of spectral sequences. There's a spectral sequence on this side. There's an algebraic spectral sequence on this side, and you compare both spectral sequences, but it uses a particular splitting of the E2 page of the spectral sequence. So it uses a splitting of the E2 page as a tensor product. This hypothesis is not satisfied in general when your space is not simply connected. Okay. However, this does not mean that the statement is not true in general.
What does that mean, splitting the page as a tensor product?
It means, okay, so it means when the space is simply connected, the second page of the spectral sequence has a certain form.
The E2 term, the vibrated thing.
As a
understand that, but a tensor product of what? Two different pages or what?
No. The E2 page, the terms of the E2 page is a sequence of groups.
Okay.
Each one splits into two,
Okay.
into the tensor product of two groups. Okay. This does not hold in general when the space is not simply connected. Okay. And as I said, this does not mean that the statement fails in the connected case. Okay. In fact, 60 years later, by taking a close look at this statement, we obtain the following subtle answer. Okay, so this is joint work with Mahmoud. So statement is that the singular change functor considered as a functor from pointed topological spaces to connected DG coalgebras, since maps between spaces which are weak homotopy equivalents, namely maps between spaces which induce isomorphisms in homotopy groups. So since weak homotopy equivalents of spaces to certain type of quasi-isomorphisms of coalgebras. Okay, I'm going to call these co-bar quasi-isomorphisms. Okay, what are these? So a map of coalgebras is a co-bar quasi-isomorphism. So a map of coalgebras is a co-bar quasi-isomorphism. So I'm going to abbreviate by co-bar QI. If the induced map at the level of co-bar constructions is a quasi-isomorphism of differential graded algebras. I'm going to remark in a second that this is not equivalent to F being a quasi-isomorphism of coalgebras. Okay.
Stronger.
Stronger. Yeah, it's stronger.
Uh-huh.
That's the first. Mark?
Is that kind of the new point?
This was observed in the literature, but it was not applied in the context of topology.
Right, but that's
Yeah,
underlined, it's not appreciated.
yeah, definitely. That's the first observation. Second is the following extension of Adam's theorem. So, for every pointed connected space, Adam's same map, which went from the co-bar construction of your singular chains to the cubical chains in the base loop space, is still a quasi-isomorphism of DG algebras. So maybe exclamation point. Even in the possibly non-simply connected space, this map is still a quasi-isomorphism. So what are the subtleties here? So let me make some remarks. These are important
This is
remarks.
like a geometric statement in some sense.
This map is completely geometric.
I mean,
For every monomial of singular simplices, you have a singular cube, and the construction is geometric. Okay. So what are the remarks here? The important remarks. First, this new notion of equivalence, co-bar quasi-isomorphism, implies quasi-isomorphisms. So this means that a map which is a co-bar quasi-isomorphism is a quasi-isomorphism of coalgebras. However, it's a stronger condition, not the other way around. Okay. So we have to be careful which model we use for your space when you plug into the co-bar construction. For example, if we take a triangulation of your space and we extract a chain complex of simplicial chains, we have examples when the co-bar construction does not compute the right homology. So the fact that this is computing the right homology is related to the fact that singular chains come from a concomplex model of your space. Concomplex means that you have inverses up to homotopy for your one simplices. Okay? So you somehow have to add these to whatever chain model you have for your space. Okay. maybe a comment about the proof of this fact. How do we avoid using spectral sequences? So the proof uses an isomorphism. Strict isomorphism between the Kovar construction and the cellular chains on a cubical complex I'm going to denote it by omega square of x. This is a new space built out of gluing cubes, which is homotopy equivalent to the base loop space. Okay. So how do we prove this? We prove it essentially at the space level. Right. Given a monomial here of simplices, we get a cube, and the differential,
Cube of loops.
a cube of loops, right, but an abstract cube first.
Yeah.
The differential here tells you how to glue these cubes. You get a cubical complex, a space, and we can show at the space level that that's homotopy equivalent to the base loop space. So we avoid using spectral sequences which are algebraic. Right? That's the essence of the proof. And then we formulate this in the language of higher categories and so on, using the work of Jacob Lurie. I think this is the heart of the argument.
I mean, this other space here has some nice categorical interpretation.
Right. You can forget about your base point, right?
Oh, you can't?
Right. If you forget about your base point, you get a topological category.
Oh,
The points of your this topological category are the points in the space. For every 2 points, you have a space of paths.
okay.
So this can be formulated in that language of higher categories, using constructions of Jacob Lurie and so on.
Like he has this BMS article about Goldman math study, what is an infinity category?
Yeah.
Sort of that idea plus stuff.
Yeah.
Okay.
I mean, this is a differential graded category with one object.
Right.
Another remark, which is important, is that now, since this theta is a quasi-isomorphism and induces an isomorphism in homology, so the zeroth homology of your Kovar construction is isomorphic to the zeroth homology of the base loop space, which we know is isomorphic as an algebra to the fundamental group ring. I'm just going to denote it by z bracket pi 1 of your space. So, the fundamental group ring of a group, the group ring of the group ring of a group is more than just an algebra, right? It's a bialgebra. Okay. So, first, the fundamental group ring is an algebra. It's a unital algebra. Let me give the names to the product, maybe star. There's a product. And there's a unit, which I will denote as eta. A unit is a map from the ground ring to your algebra. It's a unit. It's a unital algebra. Moreover, there's a coproduct structure.
One just goes to the identity element of the group. So
One goes to the identity element in the group. There's a co-unital coalgebra as well. So you have a coproduct, which I'm going to use nabla now because I want to reserve delta for the coproduct of the underlying coalgebra. So how is this defined? It's defined on generators to be the diagonal map. Right? So for any generator in your group, you declare your coproduct to be exactly the diagonal map, and you extend linearly to your fundamental group ring here. Moreover, there's a co-unit. So a co-unit goes from your coalgebra to the ground ring. In this case, it's defined by declaring every generator to go to 1 here. So epsilon of G equals 1 for all G in the underlying group. And these structures are compatible. This coproduct is a map of algebras, where the algebra structure is given by this product,
which is the group multiplication.
which is the group multiplication. Moreover, the co-unit is also a map of algebras, and the unit is a map of coalgebras. So maybe I'll write it here. These structures are compatible. So algebra plus coalgebra are compatible in this sense, and we call this structure a bialgebra. Okay. Moreover, this bialgebra admits a self-map called an antipode. So this is a property, it's not structure. So this bialgebra admits an antipode. An antipode is a map which goes, in this case, from the fundamental group ring to itself. It satisfies the following equation. So if we apply the coproduct first, then we apply the identity tensor S, and then we apply the product. We get the composition of the unit, the co-unit, and the unit. And we get the same thing if we flip the identity with S. Okay, so maybe I'll write it here. It's called an antipode. So this piece of structure is called a Hopf algebra. Okay? A bialgebra admitting an antipode. Okay, so the fundamental
Which
group.
is unique, so it's a special kind of bialgebra. It's not an additional structure.
No, I said it's a property.
Right, I want to emphasize that.
Yeah.
The way you just said it, the English was the same.
Yeah, it's a property. Admitting an antipode is a property. Antipodes are unique. Okay, so we now want to, or I will now explain how to lift this bialgebra structure to the level of Kobar construction. Okay. This is just the zeroth homology of the Kobar construction. Okay, so there's a way of prolongating this structure to higher dimensional chains. Let me describe that. So the Kobar construction is already a differential graded algebra. I want to describe a compatible coproduct on the Kobar construction, making it a bialgebra. So DG bialgebra in the Kobar construction. So this coproduct really comes from the fact that the cobar construction is isomorphic to the cellular chains on a cubical complex. The chains on a cubical complex, on any cubical complex, has a natural diagonal approximation. So let me describe that diagonal approximation, or the idea behind it. So the idea is that if alpha is 0Q, you can define your coproduct to be group-like. That's the word we use. If alpha is a one-dimensional cube or an interval, then we can define the coproduct to be the first vertex of alpha, tensor alpha itself, plus alpha tensor the second face of alpha. Right? So the picture, you have an interval. The coproduct of an interval goes to the vertex 0 times the interval itself plus the interval itself times vertex 1. And now you can extend inductively as an algebra map using the fact that cubes are products of intervals. As an algebra map using the fact that In is the product of n intervals. Okay. So this picture gives a coproduct on the cellular chains of any cubical complex. In particular, since cobar construction is isomorphic to a cubical complex, it gives a coproduct on cobar construction, on the cobar construction. So let me write that down. I'm going to write the cellular chains. So this induces a coproduct on the cellular chains of this cubical complex, which I denoted by omega squared of x, which is isomorphic to the cobar construction. Making it a D differential graded bialgebra such that the zeroth homology of this is a bialgebra admitting an antipode. Such that the zeroth homology, I'm going to abbreviate that as is HOP. Okay. So it's a differential graded bialgebra with this property. Okay, so now we're getting closer to what I wanted to explain of how to extract the fundamental group from this structure. So recall that we have a functor. I'm going to call it curly G from the category of Hopf algebras, the category of groups. Okay? This is called the group-like elements functor. Okay, so if I take a Hopf algebra H, I can output the set consisting of all elements G and H such that the co-unit of G is 1 and the coproduct is given by the diagonal map. This set has a group structure given by the multiplication of H. The unit is given by the unit of H. And inverses are given by the antipode of H.
G.
Of H. In particular, you can check, it's an exercise, that the group-like element of the group ring of a group gives back the original group. Okay. So now let's put all these pieces together. Into a math statement. So,
About 5 more minutes.
okay. So theorem also in work with Manuel. So first of all, the singular change functor, as I said, sends weak homotopy equivalents of connected spaces to, so there's a category of connected DG coalgebras, to this stronger notion of equivalence called Kovar quasi-isomorphism. So this is the notation we use. So it's called this C star. This is the singular change functor. I already stated this fact. Since weak homotopy equivalences to these Kovar quasi-isomorphisms. And the statement is that there exists a lift. Maybe I'll call it C star omega to the following category, which I will call B coalgebras. Again, with this strong notion of weak equivalence. There's a forgetful functor here. So what are B coalgebras? So let me define here what the category of B coalgebras are. So B coalgebras, this is the category of connected differential graded coalgebras C with a DG coalgebra structure under Kovar construction. Compatible with the product of the Kovar construction, so making it a DG bialgebra such that the zeroth homology is Hoff. Okay. So there exists a lift.
So this is a definition, and
Yes.
spaces go into that definition.
Yeah.
Geometric spaces go into that definition.
So, and this lift satisfies the following property. Namely, it determines the fundamental group functorially. What does that mean? So that means that the fundamental group functor, so such that the fundamental group functor is isomorphic to, well, I apply chains, consider with this structure, then I take the Kovar construction,
Wait, does that symbol mean C star omega?
the lift of this map.
Oh, lift.
Yeah. I apply the Kovar construction, I get a differential graded bialgebra with this property that the zeroth homology is Hoff. I take H0 and I take the group-like element functor. So maybe as a corollary,
So
yeah.
I just want to feel it. So there's
Yeah.
a space this is some kind of enhancement of sort of the original Kovar construction.
right? The polar construction of the singular chains has this structure of a coproduct, making it a bialgebra. Right? This bialgebra has the property that the zeroth homology is hot, and I can determine the fundamental group punctorially. So maybe as a corollary, we could state, corollary, the Kovar quasi-isomorphism type or weak equivalence class of the chains considered with this extra structure in the Kovar construction, so of C star in the category of the coalgebra, determines the fundamental group of your space. Okay? And in the last minutes, let me say that this structure of a coproduct at the level of Kovar is part of the infinite homotopical co-commutative structure of the underlying coalgebra.
The chains on the space.
Sorry?
Of the chains on the space.
Of the chains on the space. In other words, there's a further lift of this functor to connected coalgebras with infinite homotopical commutativity. And this lift determines the entire homotopy type of your space. Okay? This statement was known for simply connected spaces by a result of Mendel. Okay? But this
Less than 60 years ago.
15 years ago, actually.
50?
15, yeah,
15,
Mendel.
yeah, okay.
Yes. But this part of the fundamental group was missing, right? But it was missing because we did not have the right homotopy theory in place, right? The key is that there are these weak equivalences which are stronger than quasi-isomorphisms. And under this notion of weak equivalence, then we obtain the fundamental group. Thank you.
Questions? We have tea today, so I know everyone's nervous to get up there. We're all here, so.
Yeah.
Can you see, so pi 1 acts on the higher homotopic groups.
Mm-hmm.
Can you see this action in this first lift, or do you have to go to the next lift?
You have to go to the next lift to see this action. Yeah, there's an equivariant statement of the theorem of Mendel incorporating this pi 1 action. Yeah. Actually, at this level, you can determine algebraically the universal cover of your space.
So what do you do next?
Next is so I said at the beginning that our original motivation was to study geometric spaces, right? So there's this algebraic surgery theory of Renischke, which tells you algebraically when is a homotopy type represented by a topological manifold. And we would like to describe an algebraic structure, enhance this algebraic structure encoding the homotopy type with more structure. This more structure should take the form of a local point-carrier duality. Enhance it more such that we obtain an algebraic structure which determines the homeomorphism type of a topological manifold. I think all the pieces are in place now. This is a question that Dennis has been talking about some time.
I gave up.
He did.
All right. Okay.